happy to have Yidun, or one Yidun, telling us, okay, Dr. Yidun one from Topological Institute, telling us about twisted gauge theory models of topological bases in free spaces.
Thank you. First of all, thanks the organizers. That means including myself. Actually, in particular, thank Professor Lin, who generously invited me to co-organize this workshop. Yeah. Cool. That's right. Yeah, thank you. Thanks, Professor Lin, who generously invited me to co-organize this workshop. It's a very inspiring workshop. And today, my topic. Yes, should be on. So today I'm going to talk to you, introduce a recent work by me and collaborators, Zhu Wen, who is a student of Professor Wen, Zhu Wen Wang, and also Ge Huan. He's now currently a PhD candidate at Princeton. So, and this model, this is a model of topological phases in three-dimensional space, or 3+1 dimensional space-time. And why are we interested in such models? It's because I think I should say that a huge advantage I took to speak in the end is that lots of speakers have made introductions to most of the fundamentals of topological phases. So I wouldn't need to emphasize how important and the properties of the topological phases. But mostly, the study of topological phases focuses on two-dimensional space, or 2+1 dimensional space-time. But in reality, it's more three-dimensional material is more available than pure 2D material. And also, if you have a 3D material, you might get some surface states which are also topological. Okay, so this is a practical reason why we are interested in 3 dimensions. Not to mention that 3 dimension is our physical dimension. And also from some symmetry considerations, because in 2D, these topological phases, they exhibit a very generalized hidden symmetry, in the sense that the topological sectors, or nicknamed anyons, they took representations in a very large mathematical structure called quantum groups, or quasi-triangular Hopf algebras. So we wonder, if we go to higher dimensions, can we still have similar like hidden symmetries, generalized symmetries? So these are the more theoretical consideration or motivation why we want to look at higher dimensions. And recently we have seen that there are lots of theoretical proposals of how to classify higher dimensional topological phases. So we would like to see if we can really construct exactly solvable models, Hamiltonian models of topological phases in these higher dimensions. So what's the starting point? The starting point, like what I said, is about the classifications. Now we know that there is so-called group cohomology classification. Group cohomology classification, as you have been exposed to in the past few days. Group cohomology classification of topological phases. Then the question is, can we possibly write down a Hamiltonian model of topological phases that exemplifies the group cohomology classification? This would turn out to be actually not so possible, because this classification turns out to be a little redundant, because the different elements in the cohomology group of certain group may give rise to the same topological phase, as we will see later. So, but let's just naively think, is it possible to do so, write down a model that precisely can exemplify such a classification? And this is certainly possible. And to give you the gist of the idea, I think it's better to digress a little bit back into the 2D case. Let's consider 2D. By 2D, I mean spatial dimension. I would ignore the time dimension, the temporal dimension. So 2D, and let's consider the well-known Kitaev model. The Kitaev model is a topological gauge theory model as well, but it's not so-called twisted, as we will see. So Kitaev model is usually defined on graphs. So you have these whatever lattice you like. Okay, it doesn't really matter. And these lattice, they have these group labels on the lattice. Whatever, G1, G2, G3, G4, G5, G6, blah blah. Okay. Because this is a lattice gauge theory model, so these group elements belonging to certain group, they live on the edges of the graph. And the model is composed of two types of operators. So the vertex operators acting on the vertices, and also the plaquette operator acting on each of the plaquettes here. In this case, would be triangles. And what does these plaquettes and these operators do? The BP is quite simple. They simply impose the so-called flatness condition on a plaquette. Suppose you have G1, G2, G3 here. And then it means these three guys should multiply to the identity of the group, and without changing the graph itself. So G1, G2, G3. This imposes the flatness condition. And why we need flatness? Because we are dealing with topological phases. And this is topological. There shouldn't be, the ground state should be purely topological. So there's no any like local curvature rising in each of these surfaces. And what the AV does, the AV is actually a composite operator. It's normalized by the size of the group. It's an average of a finer vertex operator acting on each vertex labeled by group element G. And what this guy does is quite simple as well. It imposes the gauge transformation. So in this usual Kitaev model, the edges are oriented. So this is V. Suppose we have G1, G2, G3, and G4 on these four edges. What the AV does is it transforms these gauge fields on this lattice, on these lattice edges, directly connected to this vertex. I forgot the convention of going in and going down, but it doesn't really matter. Let's just assume that when it goes out, it imposes a left multiplication, G1. And it goes in, let's see, make it G minus 1. G2, this is G3, and this is G2. So G2 goes out, this goes in, so G4 minus 1. So the gauge transforms the original gauge fields on the edges of the lattice. And there's any coefficient here. So now we have a room to do something, to do some trick here. Okay. So how can we encode some group cohomology into a model like this? So the idea is to twist such a gauge transformation. We can add something here as some extra twist or amplitude to such the action of this vertex operator. Okay. And actually in 2D, this leads to, if we introduce a so-called 3 cocycle, which is an element in this cohomology group, we can construct a model so-called twisted quantum double. Twisted quantum double model. The reason is that in the end, you can see that the ground states of such a model take representations of a mathematical structure called twisted quantum double. this is actually a quantum group. And the reason is that why we have such a mathematical structure, because this mathematical structure actually encodes the charge flux duality. Of the system. So which means the ground states of such a model can be labeled by two indices, a flux label and also a charge label. And these two guys are actually on the same footing. So this is why we need such a mathematical structure called twisted quantum double to describe the topological ground states of such a system. And I wouldn't go into the details of what the precise meaning of quantum double in this talk. So, and yes, I got to emphasize, because in the beginning I said the group cohomology classification is a bit redundant. And here in the 2D case, we can already see why it is redundant. Because although we begin with a 3 cocycle alpha, in the end, we will see that the model is actually more or less classified by a 2 cocycle. By a 2 cocycle derived from the alpha. So there can be the possibility that in equivalent 3 cocycle alpha and alpha prime will give rise to the same twisted 2 cocycle, and then give rise to the same model describing the same topological phase. Now, having had this digression into 2D, we can now go to a 3 dimension. So the idea would be the same. We're just going to twist the gauge transformation in a lattice gauge theory by a 4 cocycle instead of a 3 cocycle. So in this case, let's go back to 3D. So before introducing to you the model, I would like to introduce to you some basic ingredients of this model first. So in 3D, we will have a lattice made of tetrahedra instead of triangles. So on this tetrahedra, is the vertices of the lattice are actually ordered. So you can give some labels to the vertices of a tetrahedron. And these labels, they are ordered. And each edge is oriented from the larger label to the smaller one. This imposes the branching structure Professor Van has already talked about in his talk 2 days ago. And then there will be group elements sitting on the edges. To save some notation, let's just use the combination of the 2 vertices sitting at the end to label the group. Let's say group 1, 2 is in G, and 2, 3 is also a group element in G, okay, and so on and so forth. The interesting thing is that the idea of group cocycles, they are intimately related to topology. We can see that if we have a 3 complex, so a tetrahedron is also called a 3 simplex. This is a 3 simplex. 3 simplex, also called a tetrahedron. Tetrahedron. Okay. And if you have a bunch of these tetrahedra stick together, you're actually triangulating a 3-dimensional space. Okay. And if you have a few tetrahedra grouped together, they may form certain larger 3 space called the 3 complex. Suppose we have 1, 2, 3, 4, 5. Now we have 5 vertices here, right? And they are ordered. And it turns out that on such a topological structure, we can assign a so-called four cocycle omega onto this tetrahedron. It contains, this is actually a function of 4 group variables. It maps the group, the direct product of the group, 4 times into U1. We can do such an association. If we have a little different 3 complex, we would possibly have a similar one. Right, 2, 2, 3, 3, 4, 4, 5. But there's a minus sign here as on the exponent. The reason is that there is a canonical way of assigning orientations to a 3 complex. So keep in mind that such a 3 complex cannot be visualized in 3D actually. This is a 4-dimensional picture. They're actually altogether 5 tetrahedra hidden in this graph. These 5 tetrahedra, they form the surface of a 4-simplex. So, and the way of assigning the canonical way of assigning an orientation to such a 3 complexes, you can just take any of these 5 tetrahedra here. Suppose we take the tetrahedron 1, 2, 3, 4. 1, 2, 3, 4. Okay, and we use the right-hand rule to determine its orientation. This is a canonical way of determining the orientation of a tetrahedron. Okay, 1, 2, 3. You always wrap the base, any of these 4 triangles of a tetrahedron, using the right-hand rule from the least index label to the largest one. Okay, do this, and this is right-hand, so it means this 1, 2, 3, 4 is a plus. It's a plus tetrahedron, and then you append the rest of the vertex to the end, to the beginning of the list, and you count the number of permutations that it takes to permute or to move this this remaining vertex to the end, to make a pure ascending order of the list of labels. Okay, and this is obviously an even permutation, So this 3 complex is actually a positive complex. So this is why this 4 cocycle here is positive. Okay. And on the other hand, on this graph, on this 3 complex, you will see that if you use the right-hand rule, the same tetrahedron 1, 2, 3, 4 on this graph would be actually a minus 1. And if you do the same trick to permute 5 to here, it's because it's the even permutation. So in the end, you still have a minus. So this 3 complex is a minus complex. Okay, and this is why if you want to assign a 4 cocycle onto this 3 complex, you get a minus sign here. This is the convention, and this is canonical, and very easily extended to higher dimensions. You can just go higher if you like, and you use the same convention. Okay. So maybe I should repeat why this object is called a 4 cocycle. It's because there exists a so-called co-boundary operation that acts on this omega. Let's directly use this shorthand notation. G0, G1, G2, G3, G4. So after co-boundary operator acting on a 4 cocycle consisting 4 variables, it'll become something that consists of 5 group variables. And the operation is done in this way. So you write down the original 4 cocycle, G1, G2, G3, G4, and then you just append the new variable into the beginning first. But it takes a minus sign, so you put it in the denominator, G3, G4. And then this guy is supposed to kick the first guy to the second spot in the queue. You can imagine that this is actually a story told to me by Yidun. You can imagine that there is a bus that only allows 4 passengers. And then there's an extra passenger who gets into the bus from the front door. Because the bus allows only 4 passengers, so he's supposed to kick someone out. But because the bus is so narrow, you can only kick people out one by one, right? So this guy, he first gets on the bus, and then will kick the original first guy in the queue to the second location. And then he occupies the first location. So G1, G2, G3, G4. And then keep going. But this first guy is not happy, so he will kick the original second guy into the third location. And G4. And then G0, G1, G2, G3, G4. Okay. So the original last guy in the queue will turn out to be the unlucky guy who will be kicked out of the bus. Okay. This is the way how to do co-boundary operation. Okay. And this is also easily extend into higher dimensions. And this is just a co-boundary such that the original guy here is a full cocycle. Its co-boundary is supposed to be equal to 1. And then when this holds, we call this original function a 4 cocycle. So this is a 4 cocycle condition. 4 cocycle condition. And then there can be 2 4 cocycles that are equivalent to each other. If they are equivalent to each other, they're actually different. This means, or even only if omega and omega prime are different from each other by this is called a 4 co-boundary. Okay. And this one is a 3 co-chain. But you don't have to pay too much attention to this mathematical details at this moment. You just need to keep in mind that there can be 4 cocycles that are equivalent to each other. So this group, cohomology group, is actually a group of equivalence classes. And before we move on to the model, it's better for me to introduce to you 2 more concepts that are really important, which are 2 derived quantities from a 4 cocycle. You can have let's define the so-called twisted 3 cocycle. Twisted 3 cocycle. Say G. Let's use a better notation, simpler one. X, Y, Z, U. Something. It looks like a 3 cocycle, but it has an index U. And this guy is derived from a 4 cocycle, U, X, Y, Z, in the following way. You just keep moving the U to the next location. Keep moving, X, Y, and then you do an operation like this. See? And then keep going, but you don't have too much to do because you have only 3 variables apart from U. Z. You take the inverse of the product of these 3 guys. X, Y, Z. The reason is that this guy's called some twisted 3 cocycle is because it has a similar co-boundary operation, but twisted. Let's define a twisted co-boundary operation with a tilt. Let's go W, X, Y, because this is a co-boundary, so it brings in a new group element here, variable. And this is x, y, the original one. But the original one, this is the meaning of twisting. Let's separate. So you put the original 3 cocycle, twisted 3 cocycle in the numerator, but the index is twisted by this new group variable w. And then you do the same kind of bus rule. Okay. You append the new variable into the queue, but you stop twisting the index. Then w, x, y, z, u, w, x, y, z, u, w, x, y. So z is kicked out of the bus. So this is a co-boundary operation on a twisted 3 cocycle. This is because of this twisting of the index here. It is called a twisted cocycle, twisted 3 cocycle instead of a usual 3 cocycle. And moreover, you can derive an even more tricky object. It's called doubly twisted 2 cocycle. And this is the most important mathematical object in this, which defines the model. So this one, let me write it here because it's better to keep its definition. This guy, let's call it x, y, u, w. It takes 2 indices. And this is derived from a twisted 3 cocycle. So I put a twisted 3 cocycle here, which was supposed to be w, x, y, u. And then you move w to the end, one by one, step by step. So you got x here, but you conjugate w. But you need to only to do this twice. X, y bar, w, x, y, index here. So this is so-called doubly twisted 2 cocycle. And I would like to give it a better notation for later convenience. U, W, X, Y. This is a doubly twisted 2 cocycle. Okay, having introduced these ingredients to you, we can now move on to the model directly. So the model will just look like the same. So this model 3D is also quite simple. It consists of 2 types of operators, vertex operators and also the face operators, okay, acting on the lattice consisting of the tetrahedra. And what the BP does would turn out to be the same. So BP only, this is BF, sorry, only acts on triangles, for example, 1, 2, 3. And I ignore the arrows because you know the orientation already. This is simply delta 1, 2 times 2, 3 times 3, 1 is the identity object. Identity group element 1, 2, 3, without changing anything else. So this is still the flatness condition. And keep in mind that 3, 1 equals 1, 3 inverse. So what's interesting about this model is the operators A1,